Pote, I'll let you take the stage and begin the talk.
Yeah. All right. So, good afternoon. My name is Nantikan Pratuma, and I would like to present to you my senior thesis relating to modal frequency and stress strain analysis of reference cavity. Next slide. Oops, sorry. So the general concept of this study ties into ideally the immensely precise and accurate time interval of an atomic clock, which is one of the main applications of the reference cavity. This is this precision mainly relies on the stability of laser frequencies and the efficiency of the reference cavity itself. The findings of the study will delve into how the structure of the reference cavity is influenced by both internal and external vibrations. But before I discuss these analyses, I would like to firstly expound on the process of laser frequency stabilization. So in the simplest form, an optical reference cavity consists of two highly reflective parallel mirrors that are facing each other, separated at a distance L. The light in the reference cavity reflects multiple times, producing modes with specific resonance frequencies. The process of laser stabilization can be observed when it satisfies the standing wave condition as shown here, where L represents the length of the spacer between the two mirrors and lambda represents the wavelength of the light incident to the reference cavity. Since wavelength is inversely proportional to the frequency, the condition can be rewritten to distinguish the relationship between the length of the spacer and the frequency of the incident light, as shown here. This displays that the length of the cavity is inversely proportional to the frequency at which the light will oscillate within the cavity. Now let's consider if the length changes with respect to time, then in turn, the frequency is also a function of time, which is what we want to avoid since we want the frequency to remain constant. Now we can rewrite the equation by doing the following, and we would have here a ratio comparison between the length of the spacer and the frequency. So the length noise of the cavity will create a rho nu, which is the frequency noise. Therefore, to ensure the frequency stability, the length of the reference cavity has to remain as constant as possible. Next. In order to maintain this, we have to consider the frequency noise induced by the laser itself. So the noise is observed by a phase noise where in a time domain, the sinusoidal graph appears to have a slight shift or hiccups as seen here. And by applying the Fourier transformation, we would have a frequency domain that displays sharp peaks. And the noise would just display a sort of spread around the peak. When we have a noise spectrum, we can convert the frequency noise data by applying the following schematic for locking a cavity to a laser. And as shown here in the figure, as the laser shoots towards the cavity, it is directed at an angled mirror which splits the laser, and it's directed towards a photodiode at D. And then the photodiode produces a current that that creates a certain amount of voltage input at V, which is then transferred to the piezoelectric transducer or the PZT located at Z. And this device, it adjusts the length of the cavity to match with the intended frequency. This system displays that the length of the cavity ultimately depends on the voltage input, which that is supplied by the frequency noise data. However, this system leads to the very issue that I will be mainly talking about now, which is vibrations. The piezoelectric transducer in the previous schematic is one of the sources of vibrations, which is what the reference cavity is exposed to. So vibrations are a major contributor to structural deformations of a reference cavity, which is what we intend to avoid during its usage. So in order to determine a certain solution, the causes of vibrations need to be acknowledged. So there are two main causes of vibrations. There's the vibration that is caused by the structural design of the cavity, and there's the vibration that is caused by the external sources. But firstly, the physical structure and material properties of the cavity contribute towards that internal vibration of the cavity. Now, when the reference structure induces a certain modal frequencies, it displays a variation of deformation in its shape that is also known as modal shapes. However, every object with a specific material composition will oscillate at a particular frequency called a natural frequency. When the natural frequency is excited, the object will undergo deformations that will be considered drastic for an instrument like a reference cavity. So for the case of the study, the length of the cavity will be greatly impacted by the fundamental mode, which is the mode at which the natural frequency is excited. To graphically visualize this, we can display a change in length of the cavity with respect to time in its fundamental mode as a sinusoidal pattern. A Fourier transformation can be applied here, and we would have an amplitude plot with a frequency domain. Now, the amplitude of the oscillation could be analyzed, but the effects are so drastic that the focus would have to be at the frequency at which this peak occurs. And this peak would be a concern if it is within the range of the cavity's operational usage. So a solution would be to shift this peak higher to a higher frequency past the range of the operational frequency. And since the natural frequency of an object depends on the object's composition, the study aimed to tackle this issue by changing the shape of the cavity and the material properties. So, modal frequency results. Firstly, we covered the brass rectangular cavity, and its dimensions are 20 by 40 by 77 millimeters approximately. The design has a hole through the length of the spacer, separating the two mirrors at each end. The bottom section of the spacer has a thin rectangular gap separating the two legs. But for the purpose of the study, the annular caps at the ends, they're the thin cylindrical plane that is located on each end, will be ignored since the thickness will have a minimal impact on the natural mode of the cavity. The modal frequency study that was studied, we conducted over approximately 80 modal frequencies, but I will be focusing on the fundamental mode as it is the most significant to the cavity's deformation. So in its fundamental mode, we have a modal frequency of 21.40 kilohertz. Most of the lower modes are merely translation modes where the cavity does not deform in any way and just moves in a certain direction or oscillates in a certain direction. Other modes they consist of twists and turns that do not impact the length of the cavity. Here is the simulation. So in this simulation here, it cuts off at half oscillation, but the idea is that it oscillates along its length, inwards and outwards. And this is how it looks like. So by comparing this to the analytical model, we take a look into Roerch's formula for natural frequencies. And here we have K of n, which is a constant where n is the mode of vibration. And A is the cross-sectional area along the length of the cavity. E is the Young's modulus of the material of the cavity. G is just gravity. W in this case would be the weight of the cavity per unit length. So it is mg over L. And the conditions for this following equation is that the uniform bar and spring has to vibrate along the longitudinal axis. And one end is fixed, the other end is free. So to mitigate the second condition, for the constraints, the calculations that is used will be half the length of the cavity, where the middle of the cavity is the fixed section of this model. So after plugging in the details with the constant K being in the first mode or the fundamental mode being equal to 1.57, after that, the calculations results are the natural frequency was equal to 21.94 kilohertz with an error of around 2.42% from the simulation results. Now, finally, comparing this to the noise spectrum data provided by the National Institute of Metrology of Thailand and IMT, we can observe sharp peaks located at specific frequencies. And the fundamental mode peak will represent the first major peak. Since it represents the first peak because it's the most drastic. And this occurs at approximately 23 plus or minus 2 kilohertz. And comparing to the simulation results has an error of around 7.38%. And this is the brass results, or brass rectangular cavity results. We now move on to another model design, which is the in-bar cylindrical model. And the structure is a hollow cylinder. And this study analyzed two different lengths. We analyzed a 7.5 centimeter cavity and a 5.0 cavity, or 5.0 centimeter cavity. In its fundamental mode, the 5 centimeter cavity had a modal frequency of 41.189 kilohertz, while the 7.5 cavity had a modal frequency of 27.6 kilohertz. Now, the simulation for both are basically identical, but this is an example of the 7.5 centimeter cavity, and it oscillates along its length as usual. When we compare this simulation result with the analytical model, once again, we use the same formula with the same condition, and we would use K1 equal to 1.57 because we are representing the fundamental mode. Now, for the 5.0 centimeter in-bar cavity, we have a natural frequency of 41.55 kilohertz, error of approximately 0.88%, and we have the 7.5 centimeter in-bar cavity with a natural frequency of 27.7 kilohertz with an error of 0.38%. Now, notice that the body mode of in-bar cavity is now higher compared to the brass model. So some key takeaways. So from the results, it is evident that the analytical model of the natural frequency is a valid representation of the results from the simulation with significantly low error percentage. So if we aim to increase the natural frequency of a certain object, we can apply our knowledge of the Roerch's formula to see significant relations that impact the natural frequency. So this formula, the Roerch's formula, can be rewritten by doing some variable adjustments, and we would have this relation here. And this shows that both density and length are inversely proportional to the natural frequency. So decreasing density and length can help shift the natural frequency higher. However, recall back to the process of laser stabilization. If we re-express the comparison ratio, we had to choose between a shorter and longer cavity. The longer cavity would be preferable as that would contribute more towards the reduction of frequency noise if we're able to fix the change in length. Now that the vibration caused by the structure of the cavity has been analyzed, we will now look into the second cause of vibration. Vibrations that are induced by external sources. These vibrations are impactful to the structure of a cavity, as the vibrations could be directed and coupled in all sorts of directions. External sources of vibrations could be measured to a device that is analogous to a seismograph, and it provides us with a graph of the ground's position over time, and where the derivative of the graph with respect to time will give us a velocity and eventually an acceleration graph. The accelerometer, for instance, could directly display an acceleration plot. Now, once again, we can apply the Fourier transformation. It could be implemented to display an amplitude Fourier plot with a frequency domain. Now, when we compare this is significant because when we compare this plot with the natural frequency peak, the seismic vibrations, they occur between the DC or the direct current frequency and the natural frequency of the fundamental mode. This explains that the seismic frequency will not excite the natural frequency of the object, but the cavity will still experience deformations due to the external vibrations. So The vibrations from the ground can be represented in a certain gravitational load G acting on the gravity, or sorry, on the cavity within a quasi-static mode, which is a mode where the effects are only applicable when the shaking frequency is lower than the fundamental mode. This quasi-static mode will have a certain change in length from a load G. Fusion 360, which is the computer-aided design that was used to help with the study, it applies this conversion factor, the change in length per G, which the amount mainly depends on the setup of the cavity support system. Therefore, we have a conversion factor that can be used to convert an amplitude Fourier plot to be a length plot or change in length plot. And the change in length effect will be approximated to be roughly linear via Hooke's law. For instance, if the change in length with respect to a load G, and we applied a 10G load, it would apply a multiple of 10 to the change in length. Now, ideally, we want the change in length to be 0. And the study attempts to minimize this by determining an optimal position for the cavity on a support. So for our stress strain results, we have we started off with a support design, and the cavity support system will utilize a 7.5 centimeter INVAR reference cavity, which I mentioned earlier, and a 0.5 millimeter thick V-groove support. The support angle that will be used is 30, 45, and 60 degrees, and the angles are measured from the vertical tangent point on the cylinder or the cylindrical surface to the contact point between the cavity and the support. This will be equivalent to the angle of the V-groove support itself. For each of the selected angles, the position of the groove will be adjusted and the displacement will be measured from the edge of the cavity to the support. Now, since the support has a thickness, the measured displacement will be in the middle of the support, which includes half of the support thickness. Now, depending on the setup of the cavity support model, the edges of the cavity will either tilt inwards or outwards. The study aims to ensure that there's minimal tilt along the edges of the cavity. And here is an example in the Fusion 360 software. The color-coded spectrum can be used to measure the longitudinal displacement. In this case, it's the Z direction at each or at certain points along the edge of the cavity. So here I would use the bottom point on the edge of the cavity, the inner point here, and the upper point there, and top point on the edge of the cavity. And I would use that with the trigonometry to calculate the tilt angle of this cavity. So after careful inspection of the contact condition, the loads and constraints through simplifying the cavity, the tilt angle was plotted against the cavity support displacement. And here it shows that the 30-degree support is shifted slightly higher than the displacement compared to the, or along the displacement compared to the other angles, but the difference between these angles are very small. The optimal position of the support is within 16.3 millimeters plus or minus 0.2 millimeters from the edge of the cavity. Now, the thickness of the support was also adjusted to be 1.0 millimeters, and the tilt angle was plotted for comparison. The support angle that was used for this study was the 45-degree support, but regardless, the difference between a 0.5 millimeter thick support and a 1.0 millimeter thick support is very minimal. Lastly, a study was done on a 30-degree cavity support system that had an applied horizontal load of G, which is 9.81 meters per second squared. And in this case, it's directed along the positive X direction. And the left figure here shows the displacement along the X direction, which shows a slight gradient as expected. The right figure here shows the displacement along the Z direction, or along its length of the cavity, where little to no length change could be observed. The contact condition in this study requires further research as the current boundary conditions were just merely a placeholder. So in conclusion, the study has highlighted two causes of vibrations and how both of them contribute to the cavity's structural deformation. The modal frequency studies provided insight into the factors involved in natural frequency, which is the main cause for that internal vibrations, while the stress-strain analysis attempts to mitigate the seismic noise or the external vibrations by optimizing the cavity support system. Although there are certain aspects in the study that may require further research, these analyses aim to focus on the essential components of increasing and the efficiency and the accuracy of a reference cavity. And thank you for listening.